So Jason Evans is the author of jemalloc, a terrific memory allocator. That's the memory allocator in FreeBSD, Firefox, and every company that I've worked at the least.
All right.
Oh, you got a mic.
Got it.
All
All set. Okay. Well, thanks for coming. Not going to be using the laser pointer given the angles here. It's probably good for you guys. Despite the whimsical title of the talk, this is actually a serious problem that's plagued jemalloc pretty much since the very beginning. Especially once we started, started doing most of my development for Linux optimization with jemalloc. So I'm going to talk to you kind of about the history of that and kind of the ongoing attempts to solve the issue. And we'll get into that a little closer to the end. I'll start talking about what I'm hoping to do to fix this issue. So breaking the talk into 5 major portions, going to give you a little bit of background and basics on jemalloc. Going to talk about what fragmentation is, dirty page purging, how they relate, and talk about all of the various major steps along the way in the clockless purging that jemalloc has done. I'm going to talk about some of the issues associated with doing clock-based purging, and then finally kind of show you a plausible plan, which I hope will work. I started jemalloc almost a full 10 years ago, or just a couple months shy of that now. Originally it was for a language runtime I was developing in grad school, and I realized once it was more or less done, or I thought it was done, that I didn't really need it very much for that language, so I set it aside, and a few months later some people talked me into integrating it into FreeBSD, which at the time did not have any sort of SNP scalability built into its malloc implementation in libc. The first version that went in, it did solve the SMP scalability problem, but it had terrible fragmentation issues. And so I ended up going back to the drawing board in early 2006, came up with something that actually worked quite well in that regard. And that's one of the distinguishing features now of jemalloc, is the fragmentation avoidance. A couple of years after that, I spent a year or so off and on working with Mozilla to improve the memory usage and fragmentation behavior of Firefox, especially on the Windows operating system, where the malloc at the time was especially bad. And for the last 5 years, I've been working at Facebook, working on, well, HHVM has been my main job, but I've spent a lot of time on jemalloc as well, especially adding introspection sorts of capabilities and also improving scalability for the large systems we have there. For those of you who have moved on to higher level languages and don't manage your memory manual anymore, this is what malloc is. You've got essentially untyped memory that is either uninitialized for malloc or initialized to all 0 for calloc. You can reallocate, and it may end up getting moved on you as you expand or contract. And then there's the manual deallocation, and then an assortment of alignment-based APIs and some other stuff like reallocf on FreeBSD. But essentially, this is, in a nutshell, this is what malloc is. It's a very simple API. There's an awful lot of complexity on the covers to make it work well. Distinguishing features of jemalloc, first and foremost, it's scalable, and I don't just mean that it scales to large systems. It remains the system allocator on FreeBSD, and so I have to pay really close attention to avoiding major memory overheads during startup for small applications. So it starts from the very small up to the very large. Probably the most damning thing you could say about it for small systems is that there's quite a bit of code, and so the footprint in terms of binary size is probably not ideal for very small embedded systems, but other than that, it does scale down pretty well. Like I mentioned a moment ago, the low fragmentation is pretty distinctive for jemalloc. It does as well or better than pretty much everything else out there in that regard. And part of the way that I make that reliability in terms of fragmentation happen is avoiding degenerate kind of complex behaviors between different subsystems in the allocator. So if you have some weird allocation pattern in an application, lots of fluctuation up and down, jemalloc will tend to go back to quiescent state during every fluctuation cycle, as opposed to increasingly making the fragmentation problem worse during every cycle. So it's as much as possible, I try to make jemalloc work that way. There are also some APIs in jemalloc that are unique to it. It has the allocax API, which is a superset of malloc. The malloc API, you can, for example, ask for 0 to lined memory. Also, you can manage arenas and thread caches, which I'll talk a little bit about later as well. The malloc API is how you can get a lot of the statistics. You can control some online things like flushing thread caches, creating new arenas, managing arena and thread cache assignments, that sort of thing. I wanted to show you the size classes. This is a good time to mention that these slides correspond to the development version of jemalloc. So this is what is going to become jemalloc 4 probably, I'm hoping by the end of June this year. So these size classes correspond to that version of jemalloc. What you've got, if you're using jemalloc right now, 3.6 is a little different for the large and huge size classes. The two things to note, there are 3 categories here, small, large, and huge. And the other thing is that size classes are spaced so that there are 4 size classes for every doubling in size. There's a logarithmic spacing, and that means that if your application does the unfortunate thing of incremental reallocating through a large sequence of sizes, you don't pay an exorbitant cost for repeatedly moving that memory as it no longer fits in the current location. The huge allocations are 4 megabyte objects and larger, so 4, 8, actually more or less multiples of the chunk size, which I'll talk about more in a moment. And then the large allocations and small allocations, they all fit within arena chunks, which I'll show you a diagram of them in a moment. I've mentioned arenas a couple of times. These are in the development version of jemalloc. This is finally 100% true. They're totally disjoint allocators, so they can operate totally independently of each other than that they allocate their internal data structures via a shared bootstrap allocator. But they are truly independent allocators at this point. They manage chunks. Chunks can be for huge allocations. So like some multiple of chunk size ends up being a huge allocation. And then the large allocations are multiples of the page size, and small, these are slabs of bitmap tracked small objects, 16 byte, for example, up to a little under 16K. An awful lot of what I'm going to talk about today is unused dirty pages and how to purge them. So an unused dirty page is a page that has previously been used by the application. We've allocated memory there, we've modified it, and now there's nothing in that page that the application cares about whatsoever. So this is dead weight, but it has a physical memory impact on the system. And so these are pages we, in an ideal situation, would not be holding on to. We'd be giving these back to the kernel to do with what it will. This is what an arena chunk looks like. This color scheme, I tried to follow it throughout the rest of the talk, so just take a moment to kind of internalize the colors here. This is a 4 megabyte chunk. That'll probably actually decrease by jemalloc 4 down to maybe as low as 256K. But we've got the header at the top. That's where all the metadata are. And then below that, you can see a couple of actual allocations. We've got a large allocation, and we've also got a small run down below, and then you can see unallocated memory is kind of interspersed there, both dirty, the light blue, and clean, that dark blue. And so all the metadata at the top, we've got it separated into 2 different metadata tables up in the header. Okay, let's move on to fragmentation. There are 2 types of fragmentation, external and internal. This talk is really concerned with external fragmentation with regard to multiples of the page. So the page runs that I just showed you a moment ago, that's really what we're worried about, is external fragmentation of those. External fragmentation, here we've got 4 allocations. Let's say these are 16 byte allocations, but we've got an entire page of memory back in them. So what are we using? 64 bytes of memory out of 4K. So the external fragmentation is extremely high in this case. The internal fragmentation, I've got 1 allocation I'm showing here that say the application only asks for 12 bytes. There's an additional 4 bytes at the end. That's the internal fragmentation. You can ignore that for this talk. jemalloc, the key way that it avoids fragmentation is it prefers low addresses during reuse. This, in the purest form, would be a first use algorithm or a first fit algorithm, where you have an array of memory and you scan it from the beginning. And you find the very first place you can possibly fit that allocation. There's some nice theoretical results that show that this behaves no worse than some other things like best fit. In practice, it works extremely well. And this is not an original idea to jemalloc. The papers go back to the 70s. And actually, it was phkmalloc, which was the predecessor to jemalloc and FreeBSD, that used this same mechanism. And at the time, it was the leader in terms of fragmentation avoidance itself. And so I ended up copying that aspect of phkmalloc and doing a bunch of other things in addition to make it just incrementally better than phkmalloc. any stable ordering would work. You could start from the top of memory or the bottom of memory. jemalloc packs toward low addresses, but you could also do this packing on a per chunk basis. There are a lot of ways you could do it that would, as long as it's stable, a stable ordering, it'll work out pretty well in practice. Unfortunately, there are some exceptions in jemalloc to this rule of preferring lowest addresses. Of course, there are these size segregated slabs that I was showing you, a bunch of 16-byte allocations all right next to each other. We won't try to fit a 16-byte allocation into a free 32-byte slot in some other slab. We will always try to find an open space for the specific allocation size class that we're looking for. So that there's a situation where you would prefer a higher address potentially just because of this size segregation. And that actually has some other benefits in terms of fragmentation. The size segregation reduces the fragmentation problems over time. Another issue is disjoint arenas. These are completely separate allocators, and so of course their memory can be interleaved. And so arena 1, arena 0, right? You might be looking for memory in arena 0. It turns out that arena 1 actually has something lower in memory available. We never even look there. Thread caches are a huge thorn in the side of the fragmentation avoidance algorithms. Unfortunately, they're just necessary. In the steady state, jemalloc is able to do most allocations without any contention, without any locking at all. It doesn't do any atomic operations, anything. And without this optimization, the performance just wouldn't be acceptable for a lot of these heavily multi-threaded applications. And then finally, the thing that really matters to this talk is unused dirty page caching delays the coalescing of these page runs. So in that diagram I showed you, you might have some unused dirty memory and some unused clean memory right next to each other. These do not get coalesced in these page run maps in the arena chunks. And so that can potentially cause fragmentation, especially for large allocations. You might not fit a large allocation into a fragmented chunk of memory, end up having to allocate yet another chunk of memory in order to service that request. There are a number of ways to purge dirty pages. This actually varies by operating system as well as by mechanism within an operating system. This all started off in FreeBSD, which has themadvise free flag to madvise. This is awesome. Essentially what you do is by calling madvise free on a range of pages, you tell the kernel, I don't need these pages. If you want them, go ahead and take them. If you don't take them, I may end up reusing them in the future. The great thing about this is it's very lightweight. The kernel just goes and marks a bit on each of these pages, and essentially it will go and reclaim them if there's memory pressure at some point in the future. Otherwise, the first time you actually write to that page again, there'll be a soft fault and it'll just clear that bit. And so the overhead in the common case is very low. The problem is that not every operating system has that, and so especially when we started working with Windows and Linux, Linux is what I've been focused on at Facebook. We have to use madvise don't need, which immediately discards these pages. And the typical way that an Unix operating system works is that the next time you touch one of these unbacked virtual memory pages, the kernel goes and zeroes a page for you, hopefully has a cache of them available, takes a zeroed page, sticks it in place, and now you've got initialized memory. It's all initialized to zeros. And this is due to privacy concerns. You don't want to get a page from some other process mapped into your process. This zeroing can actually be a serious problem. And in fact, that was a serious performance bottleneck for us at Facebook. We were spending, I'm trying to think, it was somewhere between 5 and 10% of all CPU time zeroing pages in some extreme cases. And so I've done a lot of work to try to reduce the amount of dirty page purging we do, but also we have a hack in place that is a flag to mmap that tells the kernel that we're okay with getting uninitialized memory in these mappings. We get away with that for a couple of reasons. One, we use container groups in Linux so that we don't have this privacy violation of getting memory from some unrelated process. This is memory from our own process essentially. And but this still isn't as good as madvise free because you are discarding those page mappings, and then the kernel has to go in and find one of these uninitialized pages and stick it back in place. And so there's additional work here as compared to madvise free. Here's an example of what fragmented versus defragmented chunks look like. On the left side, you can see the light blue. Those are all dirty pages or dirty page runs. And you can see some pretty high fragmentation there on the left side. So each of these columns is representative of one chunk. In this case, we have, you can see 4 different chunks that are these arena chunks that have the small and large allocations embedded in them. And then the green, these green ones, those are the huge allocations. So we've got a 4 megabyte and a, what does that work out to? 10 megabyte allocation here. On the right side, fully defragmented. So we're going to see some variations of these diagrams here across several more slides. Okay, let's talk about purging history. This is what jemalloc has done since 2006, and this is pretty incremental in most cases, so it's not quite the information overload you might be fearing. First off, why does jemalloc use clockless purging right now? The problem is that jemalloc doesn't have the ability to do asynchronous work. The only time it gets an opportunity to do anything is when you allocate or free. So everything has to be hooked into one of those allocation or deallocation events. If we put work off until some event in the future, that event may never come. It may be 10 seconds in coming. And so we have to be really conservative about putting work off. And so there ends up being this real conflict between speed and memory usage. We have to be conservative and purge a lot of this memory proactively because we might not get a chance for a long time. But at the same time, there's a good chance that application is going to want the memory almost right away, in which case we've just done a lot of extra work for no good reason. So going back to, you can see a timeline along the top here, little dots. It's going back to the original version of jemalloc that was worth its salt in 2006 in FreeBSD. We were using aggressive purging. However, it was actually disabled by default, and this was essentially compatible with what phkmalloc had done before it. Sometime before this, 2004, 2005, in phkmalloc, we disabled this advise free by default because it was actually having an impact. It's really nice, it's cheap, but it's not free. And so there were applications suffering 1 or 2% performance degradation from this, and so we disabled it by default. And so for a system where you really cared about memory pressure and never wanted to make sure you weren't swapping, you would turn this on, probably on a system-wide basis. It's a cost that you had to opt into. So a couple things here. The diagram on the bottom right, you can see there's one little red spot. That's the region of memory that we're going to purge. And then on the bottom left, you can see a diagram of the divergence between total memory and active memory. And in this case, they're the same because we're being aggressive. So toward the end of 2006, I got a report from somebody who was running the FreeBSD current that there was this real problem with, say you allocate 16 bytes of memory, but there's no place to put that in existing page runs. You have to go allocate a new chunk. That's a huge allocation. That's an M map. There's a lot of overhead there. And then you go and immediately free it, and then do it again, free it, right? So you're paying the cost of a huge allocation every time you do a 16-byte allocation on some of these thresholds. And this was a really big problem for this application. And so we had to add some hysteresis. So now we've got a spare chunk that never gets purged. And so you can see one of these chunks is never purged. It's full of dirty memory, just sitting around, being held on to for potential future use. So moving on, when I started working on Firefox, we really needed the ability to purge memory because that was kind of the whole point of using jemalloc was to keep the memory usage down. Well, we couldn't afford the aggressive purging overhead, especially since we were targeting primarily Windows and Linux for these changes, and the cost was just overwhelmingly unacceptable. And so I added a fixed cache. And this was 512 pages by default, and that sizing had to do with what a typical, several hundred megabyte Firefox application one would typically do. So this sounds a little corny. When I was going back and looking at what I had done over time, this sounded really corny going backward in time, but going forward in time, it actually made some sense because it was a real improvement over what was there before, which was we had this mechanism completely disabled because it was too expensive. Okay, one other thing here is notice we're iterating downward through the pages in order to purge. So in this diagram on the right side, it's essentially from right to left, bottom to top. That has some implications and something that we try to fix later. A little bit after that, when I first came to Facebook, we had a problem in that these applications were no longer peaking out at, say 500 megabytes of memory usage. They were peaking out at more like 6 or 7 gigabytes of memory usage. And so this proportional, or this fixed size cache didn't scale well for all these different applications we were running. So I just made it proportional to the amount of memory that was currently in use. So there was a ratio of 32 to 1 by default, so about 3% of memory could be dirty at any given time, and jemalloc would make sure to keep it below that threshold. Well, there was a problem with that, and that is I was purging downward through these chunks, and the problem is that not a lot of dirty pages would tend to accumulate in the high chunks in memory before I'd have to do another pass through and purge these chunks. And so I'd have to iterate over a lot of chunks in order to purge enough memory, and that chunk iteration was expensive. And so we switched over to using a FIFO order, so essentially just kind of a round robin of the dirty chunks, so that there would be some accumulation of dirty pages to purge, and we wouldn't have to go through as many chunks in order to get the work done. And this is the situation we were in for a couple of years. So this gap happens to correspond to the final push to get HHVM out into production, so I wasn't paying a lot of attention to jemalloc during that time. In late 2012, I switched to purging in fragmentation order, and so this is a little better in that it keeps track of which chunks have the highest fragmentation. The idea being that by purging those ones first, we're doing the most good in terms of coalescing and providing large regions, large runs for future allocation requests. And I thought this was pretty great, and I wasn't really planning to do any more work on this. This kind of felt like the final solution to me, but just last summer, Ben Maurer had an intern that he had work on a project where rather than purging on a per chunk basis, we kept an LRU of all of the dirty runs. And essentially the idea here is that when a dirty run becomes deallocated, you append it to the end of the list. If there's anything next to it that also becomes dirty and unused, they coalesce and then they get bumped back to the end of the LRU. And what happens is that there's a real opportunity for a bunch of coalescing to go on before you get to the end of that LRU. And so in practice, this reduced the number of Eventdriven we were doing substantially. And not only that, it reduced the total amount of dirty page purging we were doing by a factor of 2 in a lot of cases. So intuitively, I didn't expect this to make very much difference, but in practice, probably due to the way that we were coalescing and putting back at the end of the LRU, it actually works very well in practice. Okay, and so now we're getting into work that I did just a couple of weeks ago. I've been working on making chunk allocation much more scalable. The idea way back at the beginning with jemalloc was that arenas would handle small and large allocations, and that huge allocations were not going to be very common, and therefore they didn't need to be very scalable. So there was kind of one global huge allocator. And in practice, that's had a couple of problems. One, there are actually applications, whether rightly or not, are doing quite a lot of huge allocation. And the other issue is that this put false pressure on the chunk size up toward larger sizes. So it's been 4 megabytes for a few years now. And really the only reason that it isn't smaller, like say 256K, is because if we were to make it smaller, then that contention for huge allocation would become unacceptable for a lot of applications. So we fixed that problem just in the last month or so. And one of the things I did as part of that was to integrate these huge allocations into this dirty LRU. And so this doesn't really change the mechanics at all, except that now we've got hysteresis for huge allocation as well. And this works phenomenally well. It's really impressive how much this has improved performance. Okay, let's talk about clock-based purging challenges. I mentioned that Ben Maurer had an intern who did a project where he did the dirty LRU purging. He also worked on doing clock-based purging. He had a nice prototype that I'll show you kind of what we expected and what we learned from it. Imagine that we've got kind of this divergence between active and resident memory. And we've got some page caching going on. So we've got dirty pages that are persisting for a while. So this resident memory, the red line at the top, it just goes straight line for a while. And then at time 0, we decide we're going to start trying to converge on the actual active amount of memory. So what we start doing is we purge memory, and we expect those lines to converge within about 5 seconds in a quiescent system. That was the idea behind this prototype. little bit more detail about the prototype. It had about a 4.3 second delay. That's 2 to the 32nd nanoseconds. And the idea is we've got a timer wheel. We break up those 4.3 seconds into 32 timer wheel slots. And basically every so often we turn the wheel and we purge everything that's left in the oldest of those slots and then reuse that slot for the newest dirty unused pages. The surprise, it really increased the amount of memory we're using. And so in retrospect, this is totally obvious. And I'm a little shocked to say that none of us saw it coming. It's so simple. Here we've got two different arenas being operated on, so the blue line and the green line, and they're basically kind of interleaved memory usage. So they're both spiking up and down, but not in lockstep with each other. And so if you're doing really aggressive purging, your resident memory is going to stay pretty close to the sum of those two. But what you see here is that it's actually the sum of their peaks if you're delaying the purging. And so this is just an unacceptable overhead. Yeah, like I said, I can't believe none of us saw it coming, but that's the truth of it. Feel a little bad for the intern because we didn't end up using that for any sort of long-term thing that got integrated into the jemalloc source code. Well, what can we do about it? Can we limit the memory globally? That's probably a little bit extreme, especially when we're talking about NUMA systems where you've got node-attached memory. Really what you care about is limiting the amount of memory you're using on each of those nodes, especially if you're using the kind of the first touch policy where the first time you touch virtual memory, it actually ends up getting faulted and backed by physical memory from that node. If you're using interleaving, this actually is kind of a moot point, but we're not going to hurt ourselves by limiting this on a per NUMA node basis, at least not too much. So we want to limit on a per node basis, and I guess another thing to mention at this point is right now jemalloc doesn't have any coupling between specific CPUs and arenas, and that's something that's probably going to need to change in order to really do a better job of this. So we say that we've got a dirty page cache on a per NUMA node basis. We've got arenas associated with CPUs, and so there's this direct correspondence now between arenas and NUMA nodes. That's a change we'll need to make. One other surprise that, this hasn't actually come up because I haven't implemented this yet, but one of the issues we're going to run into is if we want to have some hard limit on physical memory usage, there are situations where we will need to purge dirty unused pages proactively, like synchronously, right as we're doing allocation in order to keep from going over our previous peak memory usage. This really kind of motivates some sort of asynchronous purging where we try to keep some breathing space there so that we're not having to do synchronous purging during allocation. I mentioned a little bit ago about the problem of event-driven versus clock-driven. If you're doing event-driven purging, you may never get that next event, and so so your memory usage can stay high indefinitely. And then kind of a corollary to that is that in the best case, you're going to have a lot of jittery behavior where your timing is not very precise, and so you can't have a very smooth decay. And in fact, I'm not sure I have this anywhere else on the slides. It's one of the problems also with the timer wheel is that if you just shove things blindly into these timer wheels and then delay, say 4 or 5 seconds before you purge, you still have this jittery purging behavior. It's just it's delayed by 5 seconds. And so it's not an ideal mechanism for purging. Now we've talked about clockless and clock-based purging. What about a hybrid? Probably not the best way to go. It's kind of the worst of both worlds in some ways, in that you might be doing too much work in one case, or you're being too conservative, or in other cases you're just allowing too much memory to accrue. If you say increase the active to dirty ratio, let's say we crank it up to where we allow 50% of memory to be dirty, that can actually work out very badly depending on the particulars of the application. Okay, let's talk about our plausible plan and what could possibly go wrong. Famous last words. This is not implemented yet, so if anybody has any suggestions afterwards, I'm interested in hearing them if you see any weaknesses. First, let's talk about kind of decay curves. What kind of decay curve do we actually want? I would argue that we probably want something that looks like this sigmoidal line. That's kind of the red line that starts off kind of flat and then drops down. there's a good chance you're going to want to reuse this unused dirty memory pretty soon after you deallocate it. So you want to wait a little while before you deallocate. This delayed linear line, the purple line there, that's a pretty good approximation for it. So in practice, this would be a reasonable thing to do. What we don't want to do is something like this exponential line where you're rapidly deallocating a bunch of memory right at the beginning, or rapidly purging right at the beginning. That's really kind of the worst thing you can do here, because you're shooting yourself in the foot for reuse in the near future. So this is all fine and good, but this is really kind of a static view of the system. And we've got an active system. There's a lot of allocation going on over time, and so we need an online algorithm. And so I'm going to show you kind of a prototype idea based on a moving maximum, but an exponential moving average would work probably just as well. It's probably a little easier to implement, so I may go that way. One side point here is floating point math, kind of forbidden here, since we have to work in the libc environment. Using floating point math is it's a real burden for applications that don't otherwise use floating point math. It turns out not to be a big issue in practice for these online algorithms. There are easier ways to do fixed point math. Here's the online decay algorithm as it would look with a moving maximum. So what we have, again, this is similar to some diagrams you saw a moment ago. We've got time 0, that's where we're at right now. We've got a 5-second window into the past, and so we're going to compute a moving maximum that basically shows what the maximum active memory was over the past 5 seconds. And our desire is to converge between the active memory and the resident memory within 5 seconds. Well, this moving maximum changes over time, right? Things fall off the back side of this window, and so our target changes, and so that changes the slope of the dirty purging that we want to do. But it's pretty easy to see how this works. Notice the slope actually increases in this example, but that's just an artifact of how I happen to draw the diagram. It could actually decrease over time. Here we are in a nutshell, the plausible plan. So we use one dirty page cache per NUMA node. As I was showing a moment ago, that's a pretty good solution when we've got first touch allocation policy. Going to have one arena per CPU. Whether we do this on a per hyper-threaded CPU versus physical core, not exactly obvious which way we want to go with that yet. My bias is toward only having one per core, but hyper-threading may actually, if we have one per hyper-threaded CPU, then we can be certain that we're not going to have any contention whatsoever. So we need to make this clock-based purging opt-in, right? We're going to be firing up threads that are doing a bunch of asynchronous work in the background. We can't just do that to some random application on FreeBSD. So this is something that people have to opt into. Fortunately, jemalloc has easy mechanisms for turning something like this on the fly. Environment variable, symlink. You can also set a symbol in your application to turn this stuff on. So it'll be easy for people to opt in, but it has to be opt-in. And then, as I mentioned a little bit ago, we have to do some synchronous purging if we hit the peak usage. So we're going to want some mechanisms in there to prevent that situation from coming up, kind of in the common case. And then one other thing that I didn't directly touch on earlier, are we going to prefer to reuse dirty runs, or are we going to just use the lowest run in memory? Right now, jemalloc uses the lowest run available in memory. It does not segregate the tree of available runs into dirty and clean ones. And this works out pretty well with the dirty LRU mechanism. And I'm hoping that we can keep on doing this because it tends to pack memory lower. The problem is that it also puts increased pressure on us to purge memory. Like say we end up using untouched pages, we have to potentially purge some memory right prior to allocation in these pathological cases. And so I'm hoping that won't end up being an issue in practice, but I don't know yet. Okay, just a couple of last things here. So there are some other uses for wall clock. One of them is to incrementally flush an arena cache. This is a little bit hand wavy because we don't have an arena cache yet. Let me tell you why we're going to add this to jemalloc. We have a pretty common pattern is to have some producer thread and then some consumer thread. So this producer allocates a bunch of memory, a request or whatever, and then passes off this request to another thread. The thread does a bunch of work, and then it deallocates. Well, the way this works right now is the producer pulls memory through its thread cache from an arena, does all of its allocation, ships the request over to the consumer thread. That consumer thread frees it back to its thread cache, but of course it's not doing a bunch of allocation. That gets flushed back into the arena, and then it goes, basically goes a round trip all the way into the arena and back out. Well, the cost of doing the actual arena allocation versus thread caching, there's a big difference there in overhead. And so by adding an arena cache, we essentially kind of short circuit the most expensive aspect of that, dealing with the arena itself. And so if we can keep this round trip within the arena cache and the thread caches, it should have a pretty positive impact on overall performance for these sorts of applications. So this is a no-brainer for wall clock based purging. We can flush these arena caches using very similar mechanisms to what I just described. One that isn't such a slam dunk, and this is one I'd really love to solve, but I haven't come up with a way to do it yet. And that is the thread caches. Ben Maurer mentioned in his talk just a little bit ago how we use LIFO scheduling, and when a thread is idle for more than, I think, 5 seconds, we wake that thread up and we flush out that thread cache and then put the thread back to sleep. That's a really powerful mechanism, and it's one that I would love for jemalloc to do automatically. The problem is that these thread caches in jemalloc are only ever operated on by that thread, and so there's no locking whatsoever. And so the problem is if we've got an asynchronous thread that's going and doing this flushing, somehow there has to be some synchronization there. And there's an obvious way to do this with 2 atomic operations per allocation in the actual allocating thread. It's probably possible to do it with 1 atomic operation, but I haven't come up with a way to do it without any synchronization whatsoever, and that may just be too high a cost to pay. So we're going to have to do some experiments and see what happens. All right, well, I love this diagram. I just wanted you guys to see it. If anybody has any questions about thread caches, maybe I can use it later. But anyway, didn't have any other excuse for it. Okay, with that, I wanted to specifically thank Ben Maurer. I've had a lot of very fruitful conversations with him about jemalloc over the past several years, but especially over the past year, a lot of this work is based on conversations we had. And then his intern, Chin-Fan Wu, he implemented both the LRU-based purging, and then he also did that prototype of the clock-based purging. So that was very useful. Lots and lots of other people have contributed to jemalloc over time. The list is way too long to actually go through. Anyway, thanks to them as well. And here's some links for more information. And then basically I'll open it up for questions at this point.